This is our final lesson in Chapter 5. We're looking at transforming polynomial functions today. We've seen in earlier lessons in our linear and quadratic lessons how we could transform functions of power 1 and power 2. So today we're going to look at rigid transformations that keep the original shape and size of the graph when the power is something other than power 1 or power 2. So let's start off with vertical translations. When we add a constant to a function, that translates the graph up. When we subtract a constant from a function, that translates the graph down. So up and down on the vertical axis or the y-axis. What happens to our ordered pairs is that x stays the same, but to the y value, we're adding that constant 4 in this example. And in the second example, we're subtracting 2 from our y value. In horizontal translations, when we want to move a graph, a parent function, to the right or to the left, when you are subtracting a constant, that moves the graph to the right. And when you're adding a constant, that translates the graph horizontally to the left. And the reason that happens is because of our argument here. This is the value, positive 3, that moves the graph to the right. And this value for x, that would be negative 5. Negative 5 moves the graph to the left. How does that affect our ordered pair? Well, we would add 3 to the x-coordinate and leave the y-coordinate. Or we would subtract 5 to the x-coordinate and leave the y-coordinate. When you do the opposite of x, so this is the opposite of x cubed, where this is negative 1 times x or negative x quantity cubed. Those mean two different things. The opposite of x reflects the graph across the y-axis. And then the negative x, or negative 1 times x, reflects our graph across the x-axis. What happens to the ordered pairs? In this first case, we change the y. In the second place, we're changing the x. So those are ways to help us remember what's happening. In the non-rigid transformations, they're going to distort the graph and change the shape of the graph. So here let's think about if we have an example, say y equals 4x cubed. We're keeping the x and multiplying our constant times the y value. When y equals 1/2 x cubed, because it's telling us our constant has to be a fraction, some number between 0 and 1, then we're keeping the x and multiplying the y, in this case, by 1/2. When we have a horizontal compression and the constant is bigger than 1, let's say we have the quantity 2x cubed, we're dividing our x by the c value, which is 2, and keeping the y. So this is telling us I have a horizontal compression by a factor of 1/2. And then our last one, we have a horizontal stretch when we have an example like y equals quantity 1/3 x cubed. We're going to divide our x coordinate by our c value, which is 3, and leave the y value alone. So we have a horizontal stretch by a factor of 3 here. Now let's move on and look at some specific examples. I've already pre-graphed the graphs to give us a little extra time. So let's say we're given y equals x cubed plus 2. That's my graph in black here. This is my y equals f of x graph. And we want to write a rule for the function that is f of x plus 3, and we're going to call that g of x. So if f of x is x cubed plus 2, this is my f of x, and I add 3 to that, then my translated graph is going to have the same shape as the parent, this being the parent graph, only it's going to be translated up 5 units. And in our graph, you can see this is the graph here of our g of x function. So instead of crossing through 0, 2, its y-intercept is 0, 5. And the parent had an intercept of 0, 2. In part B, if we take h of x and rename that as f of x minus 4 quantity, then I've got x cubed plus 2, but in place of the x, we're now doing x minus 4. So this tells me that we've translated the graph 4 units to the right. And here below you can see 0, 2 was my parent graph, my f of x parent graph. But if we translate that point 4 places to the right, then our h of x graph has been translated over to 4, 2. So h of x has the same shape as f of x, just that it's been moved 4 units to the right. Okay, moving on, in example 2, in this example, we see f of x as our parent graph and g of x as our translated graph. G of x is a vertical stretch from f of x to do 2 times f of x. That's a vertical stretch. And the factor on that vertical stretch is our c value, and the c value is 2. So we have a vertical stretch by a factor of 2. And again, if you checked your ordered pairs like we did in example 3, negative 2, 3, if we have a vertical stretch, we're changing the y value. So instead of multiplying our factor by the x coordinate, we're multiplying 3 times 2 on the y coordinate. And by checking our graph, you can see negative 2, 3 is on our black graph, but negative 2, 6 is on our red graph. And the same holds true if we pick all the nice ordered pair coordinates and multiply each y value. Those will pair up with a factor of 2, increasing on the y values in each case. Now we want to be able to combine those transformations and write a function that transforms our f of x graph in the following ways. We want to support our work algebraically, and we want to check our work using a calculator. So if we take f of x and we want to stretch vertically by a factor of 2, and then shift the parent function 3 units to the right, algebraically, that's telling me, let's call this new function g of x. We're going to have a stretch factor of 2 on f of x, but we want to shift f of x 3 units right, so we would have x minus 3 for our replacement. So showing that algebraically, we want to take 2 times x minus 3 cubed, because I'm looking up here, and everywhere there's an x, I'm replacing that x with x minus 3. And then we want to do 2 times 2, because remember the 2 is in the front. So 2 times negative 2 is negative 4 times x minus 3. And then 2 in the front times the 1 constant is 2 times 1. That gives us 2. Now, we have to expand this x minus 3 cubed. So if we expand that, that's going to give us 2. And then I'm thinking of Pascal's triangle. And in Pascal's triangle, we have 1, 3, 3, 1. So 1, 3, 3, 1. You've got x cubed, and then x squared, and then x, and then no x. And here we have 3 to the third, since we have this negative 3, and 3 to the second, and 3 to the first, and no 3. And then the signs have to alternate because of the minus, so we have 1 plus minus plus minus. So this expansion is going to be 1x cubed times 2, so 2x cubed. And then 3 times 3 is 9x squared times 2, so that's 18x squared. And then 9 times 3 is 27 times the 2 in the front, so that's 54x. And then 27 on the end times 2, so that's negative 54. Then we have negative 4 times x, and negative 4 times negative 3, and then another 2. Okay, let's put all of that together. Combining all of those terms, I believe we're going to end up with 2x cubed minus 18x squared plus 50x, and then minus 40. And that would be our red picture over here. So this is g of x, and the black graph is our original f of x. And I've shown my work and supported that work algebraically. In part B, we want to reflect across the x-axis and shift the parent 2 units down. So to get g of x reflected across the x-axis, we're going to multiply the f of x times negative 2, and shifting 2 units down, that would be subtracting 2. So g of x is going to be negative x cubed plus 2x minus 1, and then subtracting 2. So this one was a little simpler than the a term. Negative x cubed plus 2x minus 3. So there's my algebraic support. F of x is the parent in black, and g of x is the reflected across the x-axis and shifted 2 units down. So you can tell by looking at the picture, what was up here is now down here, and what was down here is now up here. So we did shift or reflect across x, and we shifted the point 2 units down. So everything went, instead of being plus 1, we shifted it down to 2 places and reflected over. So now let's look at example 6. Write a function that transforms y equals x cubed minus 2. That's the graph in black here. And we want a vertical compression by a factor of 1/2. So a vertical compression by a factor of 1/2, and we're going to move the x-intercept 3 units to the right. So this language, move the x-intercept, means that we're going to take our f of x graph and get a vertical compression. So that's 1/2 times our f of x, but we want to move the x-intercept to the right. So that's going to shift x minus 3 to the right. So here's our x-intercept, and you can see we want it to move 3 units to the right on our g of x graph. And to do that, we're going to have 1/2 of x cubed minus 2. And that x value is now going to be x minus 3. So again, expanding x minus 3 cubed, we saw earlier that's x cubed minus 9x squared plus 27x minus 27 from Pascal's triangle. And we want to multiply all of that by 1/2. So 1/2 of x cubed minus 9 halves of x squared plus 27 halves of x. And we have the 27, but we also have this minus 2. So that's going to leave us with negative 29 halves when we multiply through. And if you graph on your calculator this equation, and then our parent function x cubed minus 2, you should see that transformation, transforming this x-intercept over to the other x-intercept, 3 units to the right. Then one more example, and we'll be finished with this lesson. In example 7, we have the manufacturer of Speedy scooters found that the number of scooters sold during the year could be modeled by this function, where this is their sales function, where x represents the number of months since January, and we want g of x to be f of x minus 20. So first let's find the rule for g of x. So g of x is going to be our s of x minus 20. So g of x is going to be 0.01 x cubed plus 72 hundredths x squared plus 1/2 x plus 150 minus 20, so that's going to leave us 130. This is our rule for g of x. And if you graphed that on the calculator, you should see some kind of cubic function that passes the y-axis at 130, and the x-axis represents the months beginning from January to December, and the y-axis is going to represent the number of scooters that were sold in that year. So part B, explain the meaning of the transformation in terms of monthly scooter sales. So to me, if we have shifted 20 units down in our f of x or s of x minus 20, that's telling us that g of x is a translation 20 units down. So that means we've had a decrease in scooter sales by 20 scooters every month. So this means a decrease in scooter sales. Put that in a sentence of some way. By 20 scooters every month. Okay? And then I'm going to go back and make a little correction on my handout here. We should have had g of x should be s. This should be an s of x minus 20, not f of x, because we named our function s of x. And then our very last exercise, suppose h of x is s of x. So again, I'm going to correct this. S of x minus 3. And we want to find the rule for h and explain the meaning of the transformation. So h of x is our sales function with our x shifted 3 units right. So finding that rule, and in this case I'm not going to take the time to expand all of this. You can just enter this into your graphing calculator if you needed to analyze the graph or find other information. You could just be very careful and put all of that information in just like it stands without expanding. So we know h of x is translated 3 units to the right. And if you looked back at our graph, the x-axis represents the number of scooters sold, or the x-axis represents the months for the number of scooters sold. So we shifted 3 units to the right. And by moving to the right, January, February, March, that would tell us that we have the sales for the number of scooters. This means the number of scooters sold from March to December. Since our original function, S of x, represented from January to December. And that, my friends, is the end of Unit 5.